let's start by talking about the chain rule a bit. Just because I feel like, well, really, I feel like the chain rule is super important. It kind of is the rule to rule all rules. It is like the one ring of the derivative rules of math. It is the most important because it's kind of all encompassing. So before we get there, though, let's back it up and talk about the rules of differentiation we know so far. So really, there's a few rules. We know the power rule, which says the derivative of x to a power is that power times x to the power minus 1. And I don't know why I wrote parentheses there, but I started them, so sometimes I do that. No parentheses needed there. And I mean, I guess we know a couple other rules like the sum rule and the difference rule and the constant multiple rule. Those are rules that aren't super duper important in that we don't really use them so much as just kind of automatically use them. So like just the derivative of f plus g is equal to f prime. Wow, can I write the thing I'm trying to say? F prime plus g prime. And if it's f minus g, you get f prime minus g prime. And then we have the constant multiple rule, which is the derivative of a constant times your function is just the constant times the derivative of your function. But really, these two rules here don't get kind of incorporated into the chain rule the way the power rule and the trig derivative rules do. So let's talk about the trig derivatives. I guess we should talk about the other two rules first. Let's talk about the product rule and the quotient rule. So the product rule, let's remind ourselves of the product rule, which is that the derivative of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. And then the quotient rule looks a lot like the product rule, at least the top part does, except you have subtraction instead of addition. So the derivative of f of x divided by g of x is equal to the bottom, which I'm not writing. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom. See how that looks almost exactly like the product rule, except we have a minus sign there. Except then we have to divide by the bottom squared. We're just going over the rules we know. We're about to talk about kind of how we see the chain rule with kind of the rules we know. So the other rules we know are the trig derivatives. Those are, so what I'm kind of trying to talk about here is kind of all the ways we're able to differentiate things. So we know the power rule and we know the trig derivatives. And are there any other kinds of functions we've learned how to take the derivative of other than powers of x and trig derivatives? I don't think so, right? Because in this class, you don't talk about the natural log or e to the x until 16b. So we're not going to talk about taking the derivatives of those functions. So I think after x to a power and the trig derivatives, that's kind of the whole list of things we are able to take the derivative of currently. Now we can do a lot of things with that, but that's our whole list. So we're going to write them down real quick. So here are the derivatives we know. Trig derivatives. And we're going to kind of write both the regular version. Wow, can I write? That is, oof. It's rough. It looks not great. Sorry, my handwriting is just not always good, as you guys already know. So trig derivatives, let's write down the functions. We'll do it like this, and their derivatives. So f of x and f prime of x. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant times tangent. I should really be saying of x this entire time. The derivative of cosecant of x is negative cosecant of x times cotangent of x. Definitely should memorize these. Here's what I want to say about the chain rule. Every derivative you know or will learn, there's kind of a chain rule version of it. Meaning, if you take the derivative of sine of x, you get cosine of x. If you take the derivative of sine of some other stuff, you're going to get cosine of that stuff multiplied by the derivative of that stuff. It always works that way. So whenever you're replacing x with something more complicated than just x, you always have to end up multiplying by the derivative of that. So for example, if instead, we'll do this kind of this way, if my function would say like sine of, the typical notation is u. I don't love that because I feel like it's not very explicit in the fact that we have some sort of function of x. I'm going to write sine of g of x. So if I have the derivative of sine of g of x, it's going to be cosine of my stuff. What do we have to multiply by? Say it one more time. Not g of x, but g prime of x, the derivative of g of x. Every time you're doing the chain rule, if I'm taking the derivative of sine of something, it's cosine of the same something, g of x, and then outside of that, you multiply by the derivative of g of x. And I really, really want you to feel this, right? Like whenever you have an inner function that's more than just x, or even if it's just x, what's the derivative of just x? Right. So every time you could always be thinking of using the chain rule. If the inside's x, you're going to multiply by the derivative of x, which is just 1. If the inside's g of x, the derivative of cosine of g of x is going to be, well, the derivative of cosine of some stuff is negative sine of the stuff times the derivative of the inside stuff. Always. And so you could write down the same thing for all of these. The derivative tangent of g of x is going to be secant squared of g of x times g prime of x. The derivative of cotangent of some stuff is going to be negative cosecant squared of that stuff times the derivative of that stuff. The derivative of secant of some stuff, it gets a little bit tedious here, is secant of that stuff times tangent of that stuff times the derivative of that stuff. And finally, the derivative of cosecant of some stuff is negative cosecant of that stuff times cotangent of that stuff times the derivative of that stuff. And then just for the sake of completeness, there's also the chain rule version of the power rule, right? If you have the derivative of x to a power, that's just the power times x to the power minus 1. If you have the derivative of a function of x to a power, that's going to be the power times your function of x to the power minus 1 times g prime of x. Sorry, and I'm squeezing that in there really kind of terribly. So there's all like the regular versions of derivatives we know. There's the chain rule versions. And the only difference really is that the inside part or the argument of the function is more complicated than just x. And then at the end of the day, we multiply by the derivative of that inner function. That is the chain rule in a nutshell. I suppose I should actually write what the chain rule is in general, right? We've talked about it a million times. Really, I'm always going to use the word stuff, but kind of like the official version of the chain rule is if you take the derivative, so I guess let's write the chain rule here, and then we'll do some examples. If you take the derivative of f of g of x, you're differentiating the outer function, you're leaving the inside stuff alone, and then of course we're multiplying by every time the derivative of the inside stuff. Questions so far before we do some examples? Cool. Examples for all the time, every time. Sure. Oh yeah, we were doing some fun examples last time. I remember. So let's keep things in order, Jay. Oh, also, wait, one more thing, just quickly before, just as a reminder for everybody, you should definitely memorize the trig derivatives. And there's this nice pattern, right? Derivative sine is cosine, derivative cosine is negative sine. All the co-functions, cosine, cotangent, cosecant, have negative derivatives. And you can think of kind of tangent and cotangent going together. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared, but negative. So you can kind of think of taking tangent and secant squared and just adding on a co in front and a minus sign there. Same deal works here. derivative of secant is secant times tangent. And if you add a co to every function, the derivative of cosecant is cosecant times cotangent with a negative in front. The reason I say this is because it kind of means you can get away with memorizing less. If you can memorize the tangent and the secant derivative, you kind of get the cotangent and the cosecant derivative for free if you remember this little pattern. That's the way I think of it anyway. Okay, let's look at some examples. So let's say we want to find the derivative of, let's get a little bit nasty here. Let's say we have something like x cubed plus sine squared of 4x to the 6th power. And I can't emphasize enough, when I'm differentiating something and I have a power of a trig function, I really, really, really would rather rewrite it as, before I take any derivatives, the derivative of x cubed plus sine of 4x squared to the 6th power. At the outermost level, we're taking the derivative of some stuff raised to the 6th power. So my derivative is going to be 6 times that stuff to the 5th power. You can do this step by step if you want. It just requires more writing. We'll do it that way the same. So the inside stuff is x cubed plus sine of 4x quantity squared. And then we're going to multiply by the derivative of all that. So I'm just going to write it out that way. Although normally people would often skip this and say, I'm going to take the derivative of all of that. And then the next step, we do it. So next step, I'm still writing all this here. So I've still got 6 times x cubed plus sine of 4x quantity squared to the 5th times parentheses. Okay, the derivative of x cubed is 3x squared. And we're done with that, right? There's no more chain ruliness of that piece. On the other hand, the derivative sine of some stuff squared, well, I have some stuff squared. And the derivative of that stuff squared is 2 times that stuff to the first. Ooh, I didn't leave myself enough room here. That was a bad choice here. And then right in here, I have to multiply by the derivative of that stuff. I have to multiply by the derivative of sine of 4x. Sorry, I apologize. That's heinous looking. That's really, really gross. Gosh, I'm wow. It's scary because it's Halloween. That's why it looks so terrible. I'm trying to scare you. Yeah, okay. Sorry, not really. I'm just trying to make up excuses here. Let me try and write bigger here. It's a good idea as a teacher to not close your parentheses until you're sure you're going to be done writing stuff. So let's try practicing that, James. So let's see here. So same stuff. And then we have times. Now, this is interesting here. This piece here required the chain rule. We have a 3x squared plus all of this still in this parenthesis that's the derivative of this piece up here. So we have our 2 times sine of 4x to the first, which you don't need to write the first power there. And then the derivative of sine of 4x is going to be cosine of 4x times the derivative of 4x, which is 4. So many problems you will see have multiple applications of the chain rule. That happens not infrequently. Questions? All right, let's do a couple more examples and then we'll talk about some other stuff. Yeah, there's lots of, let's do like one more example and we'll talk about some other stuff. So why don't you all try this one? Find f prime of x for f of x equal to, let's say, sure, tangent cubed of x to the 5th plus cosine of x. Try finding the derivative of that. And again, I would recommend starting off by writing it as tangent of all of that to the 5th power, to the 3rd power. So go ahead and find the derivative of that.
Could you put the trig derivative,
Sorry, say that one more time.
could you put the trig derivative like notes like kind of on the side again, please?
Sure. There they are. Right. Let's take a look. So I'm seeing this. I'm going to say I've got some stuff cubed. Derivative of x cubed. So really, I mean, this is really what I think of, right? I see stuff cubed. I'm like, well, x cubed derivative is 3x squared. Stuff cubed, the derivative is going to be 3 times that stuff. Same as it ever was. Oops, I got my parentheses a little wrong there. You guys see that? I've written this as tangent of x to the fifth plus cosine x, but that's actually not what I wrote there. It was tangent of x to the fifth plus cosine x. Sorry if that threw you off. I apologize. It should be like that. Sorry about that. I guess I've got an extra parentheses there I don't really need. Blowing it today. So there's 3 times my stuff squared. I have to multiply by the derivative of my stuff. So most of the time when we do this derivative of stuff, we kind of just do it all at once. So the derivative of the inside stuff, well, the derivative tangent of x to the fifth, I'm going to have to use the chain rule again. The derivative tangent of some stuff is going to be secant squared of that stuff times the derivative of that stuff. Plus the derivative of cosine, I should have written the minus sign, is going to be plus negative sine of x. That is how we would do that. Chain rules within chain rules within chain rules. Let's look at one more because we got room on the page. It's not always a good reason, but it's a good enough reason. Again, if you have questions, you should stop me or be like, hey, James, what about this? I'll try to make less notational errors here. Let's say we want to find the derivative of x squared plus 5 over x cubed minus cosecant of x to the 4th power. Yes. Yeah, so exactly. So when I'm looking at this, I've got some stuff to the 3rd power here. I am thinking I have really x cubed, and the derivative of x cubed using the power rule is 3x squared. But I'm replacing the x with some stuff. So the derivative of some stuff cubed is 3 times my stuff squared. I will point out the way I'm writing it the reason I'm writing it this way instead of this way is because when I write it this way, it's more obvious to me that the power is the outermost function. And so my first derivative would be having to do the power rule. Whereas if I write it this way, it might look like tangent is the outermost function, and the derivative of tangent would be secant of something, secant squared or something. So that's kind of, in fact, yeah, now I wish I'd written a different problem. We'll do this one. We might even do one more, just kind of talk about the difference there. Here we do have the same thing, though. We have the derivative of some stuff raised to the 4th power. And the derivative of x to the 4th is 4x cubed. So the derivative of some stuff to the 4th is going to be 4 times our stuff cubed. But then we have to multiply by the derivative of the inside. So right? If that's our stuff there. Now we're going to multiply by the derivative of the stuff, which I'm going to have to use the quotient rule for because the inside stuff is a quotient. So the derivative of the inside stuff is going to be bottom times the derivative of the top, which is 2x, minus the top, x squared plus 5, times the derivative of the bottom, which is going to be 3x squared. Here I am going to be smart about this. I know the derivative of cosecant of x is negative cosecant of x times cotangent of x. So the derivative of negative cosecant is going to be plus cosecant of x times cotangent of x. Divided by the denominator squared, x cubed minus cosecant x squared. So get one. I keep saying one more, and then we'll talk about something different. Yeah. So I would, unless they ask me to do something else with it. So most of the time when your derivatives are gross like this, like on an exam, there'll usually be a section in the exam where they're like, find the derivatives of these things and don't simplify them. They're usually going to look fairly gross. Other times you might say, I want to find where the derivative has a horizontal tangent line, and then we have to find where the derivative is equal to 0. Or we might use the derivative to find the slope of a different tangent line, and then you actually have to do some simplifying. But if it's just this, if it looks kind of gross like this, I wouldn't simplify it unless there was a reason to. Let's look at one more here. Let's say I want to find the derivative of, let's make it interesting. Let's say it's going to be, sure, the derivative of cotangent of x squared plus 1 times cosine of x, all of that inside the cotangent raised to the 7th power. Terrible. It's a terrible, terrible function I've written there. Okay, so if we read this correctly, it's cotangent of x squared plus 1 times cosine of x to the 7th power. But the 7th power is inside the cotangent, right? It's not cotangent of the stuff all raised to the 7th. It's cotangent of the stuff inside raised to the 7th. So I'm thinking of this as cotangent of some stuff where the stuff is including that 7th power. All right. What's the derivative of cotangent of x? Let me ask, wait, before anyone says anything, is it negative or positive? Right, we know it's negative because it's a co-function. And the derivative of tangent is secant squared. So the derivative of cotangent is cosecant squared, but it's negative. So we're going to get negative cosecant squared of the same gross stuff. I should just write it on the next line here. Who am I kidding? Negative cosecant squared of the same gross stuff, x squared plus 1 times cosine of x all to the 7th power times the derivative of the stuff. Okay, so the derivative of the inside is going to be a little bit gross because, well, I have a product, but it's all raised to the 7th power. So I have to think of it as some stuff to the 7th first before I can think about the product rule part of it. So the derivative of some new inside stuff, x squared plus 1 times cosine of x to the 7th power, is going to be 7 times that new inside stuff, x squared plus 1 times cosine, all to the what? All to the 6th. Then we have to multiply by the derivative of the new inside stuff, right? So this is like there's my new stuff. And now we have to multiply by the derivative of that new stuff, which will require the product rule. So people always, for some reason, the product rule people tend to forget about it, kind of. The thing I would encourage all of you to try to remember the most about the product rule is there's always some pieces plus some other pieces. There is a plus sign in between the two things. So it's the derivative of the first part times the second part left alone. And then we add, and we vice versa. Vice versa is the best way to say it. We do the opposite things in the opposite way, right? We're going to vice versa it, and we're going to say x squared plus 1 gets left alone times the derivative cosine, which is negative sine. And again, if I had been thinking ahead, I would have written this as 2x times cosine minus x squared plus 1 times sine. But I didn't think ahead, and I don't want to rewrite it, so that's what we're stuck with. So all of this here, all of that is the derivative of the original inside stuff. All of this here is the derivative of your new stuff. Because we had to use the chain rule more than once. Come on in. Yeah, looking good. Okay. We're going to switch gears for a moment here, even though, yeah, let's go that way. So this would be, yeah, okay. Stop vacillating and just go to the next thing. Cool. Let's briefly talk about some applications problems. Really, the applications problems we mostly see at this stage are things about like throwing balls in the air, like physics problems, essentially. So let's look at this example. Of course, I've lost my numbering, have I? No, okay. We try to number things. It helps me keep track of things a little bit. Let's say we got the following situation. A ball was thrown straight up, which is hard to do. You've actually tried to throw a ball straight up in the air. It's not the easiest thing to do. Straight up in the air from the top of a 160-foot tall building. With an initial velocity of 48 feet per second, which is pretty fast. Fun fact, this is something that's worth knowing, I think. 60 miles per hour is exactly equal to 88 feet per second. It's kind of neat. Anyway, that's all I had to say about it. So this is a little more than 60 miles per hour, so like 30 miles per hour. That's not that fast to throw a ball, I think. Right? Pitchers are pitching like 90 miles an hour or something like that. Anyway, so let's ask some questions. The first question: what is the average velocity from t equals 4 to t equals 2 to t equals 4? You don't want to go backwards in time. How do we even to find the velocity? We need to know the position equation. So sometimes people are going to make assumptions about how much you know or don't know about how kinematics work, how the motion of objects falling in space work. There are some equations that we might be expected to know. The position equation of an object thrown into the air is typically given by the height at time t is equal to negative 16t squared plus the initial velocity times time plus the initial height. That is your general throwing an object in the air in the US system of measurement. If it was the metric system, that'd be a negative 4.9 instead of negative 16 there. Yeah. V sub 0, that's V naught, or also known as the initial velocity. So these things here are just placeholders. V naught is the initial velocity, and h naught is the initial height. Right, and the negative 16 is coming from the fact that it is actually half of the acceleration due to gravity. So in the US system, gravity is negative 32 feet per second squared. In the metric system, gravity is negative 9.8 meters per second squared. And we'll see in fact, we'll talk about that in a little bit more just here so you can see that. Because really these equations come from the fact that that is what gravity is. But it's really more of kind of like a Calc 2 thing. So we'll try not to say too much about it. So in our particular situation here, the height at time t is given by negative 16t squared plus v naught, which was 48 feet per second, times t, plus h naught, which was 160. So I want to find the average velocity, or in other words, the average rate of change of position, right? Because that's all the average velocity is. It's just how much distance you've covered over how much time has elapsed. Our average rate of change here is going to be the end position minus the beginning position, or the change in height, divided by the change in time. Let's see what that is, and then we'll kind of talk about what it means. So the height after 4 seconds of travel. Well, if I plug in 4 here, okay, I gotta do some math here. I'm gonna do -16 times 4 squared plus 48 times 4 plus 160 minus h of 2 is going to be -16 times 2 squared, so -16 times 4 plus 48 times 2 plus 160, all divided by 4 minus 2. All right, let's multiply this out. I know it's kind of gross, but it's not as bad as it looks. 16 times 16 is 256. 48 times 4 is 96 times 2, which is 192. The 160 is going to cancel with the other 160 there, so let's not even write it. And then 16 times 4 is 64, so I get a plus 64. And 48 times 2 is 96, so I get a minus 96. All divided by 2. So let's see here. That cancels with that. 64 plus 192 is 256, which cancels out that. And so I get -96 divided by 2, which is -48 feet per second. I traveled -48 feet in 2 seconds. What does that mean? It means overall my position was lower than it started. So when we talk about position here, positive values mean we're going up, negative values mean we're going down. So if I went from like a height of, say, 10 feet to 90 feet, my position would have increased by 80 feet, and my average rate of change would have been 40 feet per second. But what essentially I'm saying is I'm starting at some position up here, and then I'm going down. So my velocity, because velocity kind of has to have a direction associated with it. A positive velocity means you're traveling in the direction we have decided is positive. Negative means we're going in the direction we've decided is negative. So what this means is the ball started like up here, maybe even went up a little bit, but then fell to a lower position than it started at. That's why we're having a negative rate of change, or a negative average rate of change. All right, let's talk about the instantaneous rate of change, both at the beginning and at the end. So instantaneous rate of change is just a longer way of saying find the what. Instantaneous rate of change is just the derivative. So if I want to find the instantaneous rate of change at both time equals 2 and time equals 4, well, we can find the derivative of height, h prime of t, is equal to -32t plus our v naught, which was going to be 48. The derivative of position is velocity. So if this h of t tells you what distance you are after a certain time, this derivative tells you how fast you are traveling, right? It's the instantaneous rate of change. And the rate of change is feet per second. So if we're measuring just how fast we're going at a particular moment here. So this is the velocity at time t. So let's plug in and see what happens. Our velocity at time equal to 2 is going to be -32 times 2 plus 18, so plus 18 plus 48. -64 plus 48 is -16 feet per second. So after 2 seconds, we threw this thing upwards, right? We must not have thrown it very fast, because after 2 seconds, it's already going down, right? Like it was a weak throw, which makes sense if we think about, well, we'll get there in 1 second, I promise. On the other hand, v of 4, so I would expect if after 2 seconds, so I threw the ball up, it peaked, and then after 2 seconds traveling downward, 2 seconds later, after that, it's going to be going down even faster because it's going to pick up speed as it falls further and further because of gravity. Gravity is going to make this thing accelerate or increase its speed 32 feet per second every second. So I'm expecting this to be 2 seconds later, it should be like negative 64 more. So it should be like negative 80 feet per second. Let's actually see. So I plug in V of 4, I'm at negative 32 times 4 plus 48. Negative 32 times 4 is negative 128 plus 48, which is exactly negative 80 feet per second. Every second this ball falls, it's going to increase its speed by 32 feet per second. We're ignoring physics and like wind resistance and all that stuff. This is just math, right? Physics doesn't count. So that's kind of the idea here. And this is actually, we can see this if we talk about what the acceleration is here. So if we take the derivative of velocity or the rate of change of velocity, the acceleration, which is equal to the derivative of velocity, which is equal to the second derivative of position. If I take the derivative of negative 32t, I just get negative 32 feet per second, or people like to say feet per second squared. And the real thing that actually people do here is they start with this. They're like, well, gravity is negative 32. And then they do anti-derivatives to get back to see what the velocity is and then see what the position is.
What is A?
A of t is acceleration. Good question. Yes, I should label things. That is the acceleration at time t. And for a body that is just falling through space in the Earth's atmosphere, the acceleration due to gravity is a constant negative 32 feet per second. Again, assuming we don't have wind resistance or anything like that, like just assuming perfect conditions. That is the velocity at time t. And that is the position at time t. So, aside from finding things like the average rate of change over a certain time or the instantaneous velocity at a certain time, we could also ask questions. The two kind of typical questions people ask about a situation like this are question 1, how high does the ball go? Question 2, how fast does the ball hit the ground? Those are like pretty standard questions people ask when you throw a ball in the air. So to find either of those things, you really have to find out what time it is when those things happen before you can actually figure out how high the ball goes or how fast it hits the ground. So yeah, so let's rewrite our equations here. So we had h of t equal to negative 16t squared plus 48t plus, was it 160? It was. And v of t equal to negative 32t plus 48. And the first question is, how high does the ball go? Wow, is that the word high? Sure. How high does the ball go? Really, to answer this question, you have to ask yourself, okay, what is happening when the ball reaches its maximum height? Well, the ball was going up. Its speed, or sorry, its velocity was positive. The ball tops out, and then it's going down, and its velocity is. And if you go from a positive value to a negative value, you have to have gone through what number? 0. You have to go through 0. So to find when the ball reaches its maximum height, we're going to set the velocity equal to 0, which makes sense, right? Because the ball is going up, 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 up. It slows down, it stops, and then starts going down. So to first find the time, we're going to set velocity equal to 0. Yes, of course. Sorry. Thank you. I know. I always, please let me know. I'm always happy to adjust. It's just, I literally have it in front of me too. I just get so distracted here. So then we're going to solve for t. So negative 32t equals negative 48. That's going to give me t equal to 48 divided by 32, which reduces to 3/2 or 1.5. Great. That even that's reaffirming to me because we saw that after at time equals 2 seconds, the ball had a negative velocity. So it makes sense that it only took 1.5 seconds to get to the peak, and then after that, it was going down, 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 down. But now we were not finished, right? They didn't ask what time is it when the ball has a maximum height. They asked what is the maximum height. So then to find the maximum height is going to be when we plug in that time to the height equation. So we're gonna have to find height at a time of 3/2 seconds. So we're gonna get -16 times 3/2 squared plus 48 times 3/2 plus 160. 3/2 squared is 9/4. I can cancel a 4 there and a 4 there. 48 times 3/2 is really 24 times 3 plus 160. That's going to be -4 times 9 is -36. 24 times 3 is 72 plus 160. So I end up getting 36 plus 160, so 196 feet. That is the highest height the ball reaches. And that is usually the way we find this thing, right? If someone ever asks, how high does this thing go? First, find the time at each of the height by setting the velocity equal to 0, and then find the height by plugging that time back into the height equation. All right. So I want you to think about this for a second. If I want to find out how fast does the ball hit the ground, I first need to find when the ball hits the ground. So what's true when the ball hits the ground? What do we know about either the height or the velocity if the ball is hitting the ground? We don't know the velocity, right? We're being asked to find the velocity. But we definitely know that if the ball hits the ground, the height is how many feet high? 0. Usually these problems involve setting something equal to 0. So we're going to start by setting the height equal to 0. So first, set the height equal to 0. And the height is -16t squared plus 48t plus 160. And usually, if someone has been kind, they will set this up so that a 16 factors out. And it does. In fact, I would actually factor out a -16. So -16 times +t squared minus 3t minus 10 equals 0. And then factoring again, I've got -16 times t minus 5 times t plus 2. Yeah, that seems okay. So what time is it when the ball hits the ground? There's 2 choices. Time could be positive what? Show me on your fingers. Positive how much? Yeah, that many. Yeah, that many. Yeah. Positive 5 seconds. Or time could be what? -2 seconds, which means if you could kind of undo time and go backwards in time, like, and follow the parabola back down backwards, it would -2 seconds. Like if you could go back in time -2 seconds, that's where the ball would hit the ground. It doesn't make a whole lot of sense, but it kind of, like, if you think about the path of the parabola, because really you've kind of got this thing where you're throwing this ball off the top of this building and it's doing this kind of deal here. But if you could go back in time, that's how much time it would take to get back to like the ground as well. So great, I want to find the velocity that the ball hits the ground with after 5 seconds. Are we expecting this velocity to be positive or negative? Good question. Let's find out. So if I plug in 5 seconds to the velocity equation, I'm going to get -32 times 5 plus 48. That's going to be -160 plus 48, which is definitely -112 feet per second. Which makes sense, right? The ball is traveling downwards. And at least most people, when they set up problems like this, they set it up so the upward direction is positive and the downward direction is negative. You don't have to do it that way. You can tell people do it other ways, but that's a pretty standard setup. So I would encourage you to do it that way. All right. Cool. All right. Not cool. I would love more time. All right. We got other things to talk about. So moving right along. Let's talk about implicit differentiation. Implicit differentiation is really just the chain rule. Again, it's always the chain rule. Everything comes back to the chain rule. Let's see here. I thought I had more of it. There we go. Yes. Oh, in fact, yeah, we got sorry, 1 second. We got so many papers everywhere. Nope. No. Okay, fine. So let's take a look at this example for a second. I want to let's do it this way. Let's say we have brain x cubed plus y cubed equal to 6x times y. And I want to find the derivative of this. Well, when someone says something like this, and they say find dy dx, there is an assumption implicitly, which is why it's called implicit differentiation, being made. It is implied that y is a function of x here, or at least that y depends on x. And it's true. Could we solve for y as a function of x? Sometimes, not this time. There's no easy or even possible way to solve for y here. But the point is that we're thinking of y as some function of x. So often, at least in the beginning, instead of writing this, I'm going to write this instead. I'm going to rewrite the same problem, but instead, we've got x cubed plus a function of x cubed equal to 6 times x times a function of x. This is more writing than I really want to do, but that's okay. And so we're going to find dy dx, which now is going to be called f prime of x. And the way we're going to do this is by differentiating both sides. So what's the derivative of x cubed? No problem. I differentiate both sides. The derivative of x cubed is just 3x squared. But now the more interesting question that I know you all know the answer to because we've talked about the chain rule quite a bit. What's the derivative of some stuff cubed? 3 times your stuff squared times what? Thank you. I know it's hard to say it, but it's true. The derivative of the stuff equal to, over here I've got 6x times f of x. I have a product of 2 different functions of x. When I have a product like this and there's also a constant, I kind of like to think of the constant just attached to the first piece. So I'm really thinking of this as 6x times f of x, just because it's easier to do it that way. You could also just think of the 6 out in front. I don't love that personally. So it's going to be the derivative of 6x, which is what? Times, is it times f of x or times f prime of x? Good question. I'm doing the product rule. I did the derivative of 6x and I need the not derivative of the other piece. And then I have to add. And now I switch it, or I vice versa it. I leave the 6x alone and I multiply by the derivative of the other piece. But people don't actually write it this way because we're lazy. I don't want to take the time to rewrite y as f of x and rewrite the derivative of y as f prime of x. Instead, what we do is we're just like, well, y is like f of x. So if I was doing it that way, I would say, well, I have 3x squared plus the derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff equal to the derivative of 6x times y plus 6x times the derivative of y. It is literally the same. It's just using different letters, using y and y prime instead of f of x and f prime of x. But I hope all of you can see that, right? That could be my y. That's my y prime. That's my y. That's my y prime. It is literally the same as that. And that is the first most important step of implicit differentiation, is differentiating both sides with respect to whatever variable they're telling you to differentiate with respect to.
And they did this, and it was divided by the putting the d over dx times x.
I wouldn't say so. Don't use the word times there, because you're not multiplying ddx by x. You're saying ddx of x cubed. Right. We are totally doing that. So you could, if you wanted to, at the very beginning, say I'm taking. So if I've got, this, I'm doing the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed equal to the derivative with respect to x of 6x times y. Right. But that is a good way to know what you're differentiating with respect to. I will tell you that if someone has written a problem like this and they haven't given any instruction other than find the derivative, they mean y as a function of x, unless they've said something differently. That is the base assumption we make if someone hasn't said anything else. Unfortunately, we're not done. After you do this first step, then you have to do the algebra of solving for y prime or f prime of x. So after this first step here, then what we do is, and let's go ahead and do it this way. We then collect the terms that have y prime on one side. Doesn't matter which side, just pick a side. So I see a term with a y prime there and the term with the y prime there. You can bring them to the left or to the right. Either way is totally fine. So all my y prime terms on one side, so I have a 3y squared times y prime minus a 6x times y prime. And all the other terms on the other side. So on the other side, I'm going to have a 6y minus 3x squared. And then we factor out a y prime. So y prime, that's why we brought all the y primes to one side. So we could factor one out. So you have y prime times 3y squared minus 6x equal to 6y minus 3x squared. And finally, you divide by whatever is multiplying y prime to get y prime equal to 6y minus 3x squared divided by 3y squared minus 6x. And that is your derivative of this original equation. We're going to do more examples, but questions about this one before we do some more examples. Yeah, Peyton. Oh, sorry, Erica. Sorry, Erica, Peyton. Apologies.
So if you problem like this, you just like start doing the chain rule?
Right. Well, because yes. So when someone says implicit differentiation, you should exactly be thinking we are using the chain rule because we have stuff to powers or tangent of stuff, or right. If you see y, you should think really when you see the y in this or whatever the function thing is, which is usually the y, you should be thinking of, oh, that's my stuff. It's not just x. Its derivative isn't just one. Its derivative is y prime or dy dx. Let's do another example. But yes, you're totally on the right path there. You should think of if you see equations where you have x's and y's or y's and t's or all your things kind of mixed together where you can't just solve for y as a function of x, then yeah, you're using implicit differentiation, which means you were exactly using the chain rule. Let's look at another example here. Let's look at something like, sure, we have cosine of x plus secant of y equal to y squared plus 3x. And again, we want to find dy dx or y prime. You can write either way. People tend to write y prime just because it takes up less space in this problem. But if you want to write dy dx, that's also fine. So we're going to differentiate both sides with respect to x. And it is totally fine to do like, oh my gosh, Nikki was saying, and write ddx of everything. So you can say I'm going to take the derivative with respect to x of cosine of x plus the derivative with respect to x of secant of y equal to the derivative with respect to x of y squared. You probably don't need to write so many of them like I am, plus the derivative with respect to x of 3x. You just write one ddx on each side if you prefer to do that. All right, what's the derivative of cosine of x? It's definitely negative because it's a cofunction. It's negative sine of x. All right, the derivative of secant of some stuff. I know the derivative of secant of x is secant of x times tangent of x. The derivative of secant of some stuff is secant of the stuff times tangent of the stuff times y prime, the derivative of the stuff, or dy dx, whichever way you prefer to write. I'm going to write dy dx this time just to change it up. Equal to, okay, on the right-hand side, the derivative of some stuff squared is 2 times your stuff to the first times the derivative of your stuff. The derivative of 3 times x, you could use the product rule, but you do not need to. The derivative of 3 times x to the first is just 3 times 1, which is just 3. And just like before, I'm going to observe where I have my derivative. So these terms have the derivative in them, so I want to isolate those on the same side. I was going to bring them to the right just to change things up. I really don't want to, and here's why. I would prefer to bring things to the sides where more of the stuff ends up being positive. If I brought those to the right, then I'd bring that to the left, and all the stuff on the other side would be negative, which I just don't care for. Yeah.
Why don't we add like symbol there?
You mean right here? Because so yes, good question. So here's why. If I took the derivative with respect to x of secant of x, I would get secant of x times tangent of x times chain rule, the derivative with respect to x of x. But what's the derivative with respect to x of x? Or what's the derivative of x? Thank you. Yeah, show me on your fingers. Yeah, 1. So this is just secant of x times tangent of x times the derivative of x, which is 1. But when I take the derivative with respect to x of secant of y, same deal. It's secant of my stuff times tangent of my stuff times the derivative with respect to x of my stuff. But now the difference is, I know the derivative with respect to x of x is 1. The derivative with respect to x of y is the thing we're trying to find. I don't know what dy dx is. It is the derivative of y with respect to x, which we are trying to figure out. So that's why we have to write this here, because we had a y there, not an x. The derivative cosine of x was negative sine of x times 1. The derivative secant of y is secant of y times tangent of y times the derivative of y, the derivative of the inside stuff. The rule of like the less kind of knowing what you're doing way of doing it, but easy to apply way of doing it is just to be like, every time you have a function with a y in it, at the end you kind of multiply by a y prime. I don't love that because it doesn't really exemplify a lot of understanding, but it does work as far as like making sure you've got things right. So all the things that have y's in them, right? Derivative of y squared is 2y, slap on a y prime. Derivative secant of y is secant of y, tangent of y, slap on a y prime. Derivative cosine of x is negative sine of x, I don't need a y there. Derivative 3x is 3, I don't need a y there, or a y prime there. Now we're going to bring these things in green to the same side, and I'm going to bring them to the left. So I have a secant of y, tangent of y, times dy dx, minus 2y times dy dx. I often skip the step, or I often combine the step with the next step and also factor out the dy dx at the same time because it's not too hard to do. And then adding sine to the other side, I get sine of x plus 3. Factor out the dy dx, so you're left with secant of y times tangent of y minus 2y equal to the same thing on the right. And then divide by this, so you end up getting dy dx equal to sine of x plus 3 divided by secant of y times tangent of y minus 2y. Gross. Usually these problems are kind of gross. And it's not so much the derivatives that are gross, it's really more the algebra that is typically kind of gross for these problems. Oh, we got time. Okay. Let's do a couple more because there's usually a couple varieties of this that pop up. So let's look at this next one here. Yeah. Ooh, actually, let's look at it. Let's do one more where we don't do that. Yeah, that's a good point, James. Good catch. Let's say we had the following. Ooh, yeah, this is gonna be terrible. Not really though. I promise you, it's not as bad as it looks. So let's say we had this example. Where again, we're gonna find dy. Let's change it to dy d. No, let's not change it to dy dx for y times cosine of y equal to, oh sorry, over x plus y squared equal to 1. And things are really especially messy if you have to use the quotient rule. But you know what? For implicit differentiation, you really never have to use the quotient rule. because you are totally allowed to multiply both sides by the denominator before you do anything. It is a valid move when you've got this kind of implicit differentiation situation. So instead of starting with this, multiply both sides by x plus y squared. So we end up getting y times cosine of y equal to 1 times x plus y squared. That seems much less terrible to take the derivative of. And actually this does, well, I've seen this come up in web work, which I know is not really something most of you have to deal with because most of you are in Tabernates class, but it is something that comes up sometimes in web work. So, but generally, if you're asked to find the derivative of something terrible with x's and y's all mixed together and there's a quotient, it is perfectly valid and I would say encouraged to multiply both sides by the denominator so you don't have to deal with the quotient rule. So now differentiate as typical. I got y's here and I have a product rule over here. So if I do my ddx of both sides, I'm just gonna, yeah, let's just do that. So the derivative of y is the derivative of y. It always feels silly to say that, but it is what it is, right? The derivative of the first thing is the derivative of the first thing times leave the second thing alone. Plus, now we switch it up. We leave the first thing alone. We multiply by the derivative of the second thing. The derivative cosine of y is negative sine of your stuff times the derivative of your stuff. On the right-hand side, the derivative of x is dx dx, which is just 1. The derivative of y squared is 2y times the derivative of the stuff, which is dy dx. Okay, let's try and do two things at once here. We're going to bring the 2y dy dx over to the left, and we're also going to factor out the dy dx from everything. So we're going to have dy dx factored out, times we had the cosine of y there. We have a negative y times sine of y here. And we'll have a negative 2y when we bring that over. Equal to 1, and then dividing by everything, dy dx is 1 over cosine of y minus y times sine of y minus 2y. I don't want to do it because it's time consuming, but I will tell you that if you did this the other way, like you started with this problem and actually used the quotient rule and did the whole derivative and then multiplied everything and brought all the y primes to one side and factored and divided out, you would get the same answer. It would just be a less nice process. So a lot of times with implicit differentiation, they just ask you to find the derivative. But a lot of times they also ask you to find either the equation or the slope of the tangent line to the equation at a particular point. So let's look at an example like that and kind of talk about the ways we can do it, because there are multiple ways of addressing it. Let's say we have the following. Ooh, yeah, that's a good problem. So I'm going to go with equation. Find the equation of the line tangent to x plus y to the 5th equal to x times y plus x cubed plus y squared at the point -1, 1. Fun fact, you should never check to see if that point is actually a point on the graph, because sometimes people just make stuff up that's not right and then it's super confusing. They just want you to pretend like it doesn't matter. So even though this point should be on this curve, like if you plug in -1 for x and 1 for y, it should work out that these are equal to each other, and they are. Plug in -1, 1, you get 0 here, and you definitely get -1. Ooh, dude, nope. See, look, terrible. I said the thing, I grabbed a problem from somewhere, and this is actually not a point. What's -1 plus 1? 0. Here, -1 times 1 is -1. Plus a -1 is -2. Plus 1 is -1. Plus 1 makes it 0. So good point, James. Don't check. If you see this problem on a test, don't worry about whether or not this point is actually on the curve. It's just not worth worrying about. But it should be. All right, so now it actually is. If you plug in -1 for x and 1 for y, both sides are equal to each other, which is great. So to find the equation of a tangent line, we need two pieces of information. We need a point. Got it. And we, of course, need the slope. And how do we find the slope in calculus? By taking the derivative. So we're going to take the derivative, but the only way we can take the derivative here is implicitly. So I'm going to take the derivative, so differentiate both sides. The derivative of some stuff to the 5th power is 5 times your stuff to the 4th power times, in parentheses, the derivative of your stuff. The derivative of x is 1. The derivative of y is y prime, or dy dx. Equal to, okay, on the right-hand side, I've got x times y, which is a product rule. It's a product. I have to take the derivative using the product rule. The derivative of x is 1. The derivative of y is y prime, but I don't multiply the derivative of x by the derivative of y. I don't multiply the two derivatives together. It's the derivative of x times the not derivative of y, plus x times the derivative of y, plus the derivative of x cubed is 3x squared. The derivative of y squared is 2 times y to the first times the derivative of y. And then be careful here. It's really easy for people to write plus 1 at the end here, but the derivative of 1 is 0. So don't write anything or write plus 0. I'm going to write plus 0 for now. But for some reason, the constant there often accidentally tags along in this process for some reason. So just be careful. Okay, there's 2 ways to go here, and yeah, we have enough time. I want to show you both ways because one of them is really great and one of them is really terrible. So if this problem was just find the derivative, we would normally proceed like this. We would, well, yeah, this is extra terrible because you got this here. So I'd have to get all the dy dx's on one side, but I also need to distribute this because this kind of has a dy dx and a not dy dx. So I'm going to distribute. I'm not going to multiply out x plus y to the 4th, but I'm going to distribute that to each of those terms. I'm going to get 5 times x plus y to the 4th times 1 plus 5 times x plus y to the 4th times dy dx equal to y plus x times dy dx plus 3x squared plus 2y times dy dx. You might not want to write this part down just because it is terrible, and we're going to do it a better way in a second. Bringing all the dy dx's to the same side. Let's change up and bring them to the right-hand side for once, just to do it differently. I'm going to get 5 times x plus y to the 4th, and then I'm going to have that and that come over to the left, minus y minus 3x squared, equal to, let's factor and move things at the same time. So x plus 2y minus this part here, which is 5 times x plus y to the 4th, all times dy dx. Finally, dy dx is equal to all this junk here divided by all this garbage here. Cool. And then we could find the slope of the tangent line at the particular point by plugging in x equal to -1 and y equal to 1. People often write this in the following way. They write dy dx vertical line for evaluated at, and then down here at the point -1, 1. And we're just going to plug in -1 for x and +1 for y. So it's going to be 5 times -1 plus 1 to the 4th minus 1 minus 3 times -1 squared over -1 plus 2 minus 5 times -1 plus 1 to the 4th. -1 plus 1 is 0. These parts go away. So I end up with -1 minus 3, so -4, divided by -1 plus 2, which is 1. So I end up with a slope of -4. Okay, let me show you the better way. But I really wanted you to see the terrible way so you can really appreciate how much nicer the nice way is. I'll reiterate. If you're just asked to find the derivative, not at a particular point, you have to do this. You're stuck, right? This is the derivative just with x's and y's in it. But if you're asked to find the derivative at a particular point and not asked to find the whole entire derivative, what we should do instead is plug in your point as soon as you differentiated both sides. So the other way to do this is to say, do I have enough room? No, let's be smart, James. Instead, take your derivative, 5 times x plus y to the 4th times 1 plus dy dx. I should say, take the equation you differentiated on both sides because it's not the derivative. We haven't solved for dy dx here. equal to y times plus x times dy dx plus 3x squared plus 2y times dy dx. And just plug in xy equal to -1, 1. So everywhere I see an x, I'm going to write a -1. Everywhere I see a y, I'm going to write a +1. Notably, -1 plus 1 is 0. So this whole part's going to be 0. So plugging in, I'm going to get 0 times 1 plus dy dx. Yeah, that's right. Okay. Oh, yeah. Sure. Equal to 1 plus -1 times dy dx plus 3 plus 2 times 1, so 2 times dy dx. That's all 0 on the left, so I've got 0 equal to 1 plus 3 is 4, and -1 plus 2 is a +1 times dy dx. So -4 equals dy dx. Oh, that's the same answer I got the other way. And in my opinion, and in most people's opinion, doing it this way is usually considered to be much, much easier. It's usually, if you're asked to find the slope of the tangent line to the equation at a particular point, way easier to, after you have differentiated both sides, to plug in the point and solve for y prime or dy dx. And now to answer the question, the equation of the tangent line is going to be y minus the y coordinate equal to your slope times x minus the x coordinate, which we could simplify as y minus 1 equal to -4 times x plus 1. Y minus 1 equals -4x minus 4. So y equals -4x minus 3. So that is usually how we deal with finding the slope of the tangent line to an equation where you'd have to use implicit differentiation or the equation of the tangent line. Cool. Let's try to do, let's talk about related rates for the last 6 minutes here, because related rates definitely something we'll talk more about on Thursday, but we should talk about. And really, I will say related rates is just another kind of example or utilization of implicit differentiation and the chain rule. So let's look at kind of a very standard example. I like to think of this in the following way. So the radius of a circle, so related rates. I think of this as I threw like a rock in a pond and the circles are getting bigger and bigger and bigger. So the radius of a circle is increasing at a rate of 3 inches per second. When the circle has 25 pi square inches of area, how fast is the area increasing? Here's what makes this a related rates problem. They told you how one thing is changing, the radius, and they asked you how a related thing is changing, the area. That is why it's called related rates, because there are two rates of things that are changing and they are related to each other. So in a related rates problem, I have kind of like a 4 or 5 step method that I feel like usually works. So the first step, the 0th step that we sometimes apply and sometimes don't, is to draw a picture. Sometimes a picture is helpful, sometimes it's not really, or sometimes you really can't. Here at the circle, so I mean, sure, step 0, draw a picture. So you've got this circle, and we're thinking of the radius. And typically, I draw a picture and label the things that are changing. So the radius is changing, right? It's not set at 5 or 10 or however many inches. And it's kind of hard to label the area. Like I could shade in the circle and say there's the area, but this feels kind of silly. Okay, But the real step one, after you've thought about what's changing, is to, as my teacher used to say, identify the d what's, meaning the d something over d something. So find your d what's. Find your rates of change. What things are changing in this problem? Someone tell me one of the things that's changing. Words. The radius is changing, right? They told us the radius is changing. So we know the radius is changing. And I'm going to write that, okay, here's the important part. The radius changing, the rate of change of the radius, dr dt. There's one of my dwhat's, dr dt. How fast is the radius changing? Did they tell us? Yeah, they did. The radius is changing at 3 inches per second. What else is changing that we're interested in? I mean, so I should point out, there's a lot of correct answers to this question. Technically, the circumference is changing, and the area, and any other measurement of the circle you want to talk about, you could say is changing. But the one that I actually care about is the area, because that's what we're being asked about. So really the question should be, what are the things they've told you are changing, and what is the things they've asked you about that are changing? The other thing is the area. And so the area is changing, and we're going to say, well, we don't know what that is. We want to find it. So dA dt is something that we don't know, but we want to find. After you've identified the things that are changing that are important, the second step is to find an equation relating those non-time variables. So in this case, area and radius. Typically, it's the equation of the geometric shape you're dealing with, whether it's a circle or a cone or a square or a rectangle or lots of other things. It's usually that kind of equation. So here, our equation is just area equal to pi times r squared. But I'm going to point out that both area and radius are functions of time. So really, people don't usually write it this way, but really I'm thinking like area as a function of time equals pi times radius as a function of time squared. Step 3, differentiate both sides with respect to time. I know we're almost out of time here, speaking of time, but we're almost done. So what's the derivative of area? Well, the derivative a of t is a prime of t, or dA dt. Sorry, I'm being said a little bit better there. So I'm going to get dA dt. All right, pi times r squared. The derivative of pi times r squared is pi times the derivative of some stuff squared is 2 times your stuff to the first times the derivative of your stuff. It is literally just like implicit differentiation, where now we're assuming that everything is a function of t. And so when you differentiate it, you have to multiply at the end by the derivative of that thing with respect to t. If you look at it over here, just to kind of think of it here, you could say if I differentiate both sides of this, it's a prime of t equal to pi times 2 times r of t to the first times the derivative of r of t. It's exactly what I'm writing here. It's just more typical to write it this way. All right. And then after you have differentiated both sides, that's when you plug in the stuff you know, solve for what you don't know. So step 4, plug in and solve. I know I'm almost out of room here. I'm definitely out of time. This is usually where you have to go back and read the question. So I don't know what dA dt is. That's what I'm trying to find. So I'm saying dA dt is equal to 2 times pi times, do I know what the radius is at the moment of interest? They didn't exactly tell me that. They said, when the circle has 25 pi square inches of area, how fast is the area increasing? Well, if the area is 25 pi square inches, what did the radius have to be? 5 inches, right? They're usually telling you, sometimes they're making it really, really obvious. Sometimes they're making you work a little bit for it. So 25 pi times 5 inches times dr/dt, which was 3 inches per second. So we multiply this all out, we get 5 times 3 times 2, which is 30 pi. Inches times inches is square inches per second, which makes sense units wise, right? If you have an area that's increasing, it should be changing at a rate of inches squared per second, or some unit of length squared per second. All right, we'll talk more about related rates on Thursday. Have a lovely Halloween. Scariest thing you'll see all day.